All right, you're probably getting tired of queuing videos. Let's just look at two more scenarios. One is that if we have a single server with a constant server time, so there's no variability in the time that it takes, everyone takes the same amount of time. So then in that case, the calculations are a little bit different here, so we're just going to show that. And so we'll look at our formulas here that we have a function of lambda and mu, but there's no variability in that mu. All right, so probability the system is idle. No one's in the queue. Same calculation as we've seen before, 1 minus lambda divided by mu. The average number of units in the queue is going to depend on both lambda and mu, the arrival rate and the service rate. The average number of units in the system being served plus the queue is, of course, going to depend on the average number of units in the queue plus lambda divided by mu. Where the calculations, of course, get a lot simpler is that if we have a constant service time, then the average time spent in the queue is simply going to be the average number of units in the queue divided by lambda. The average time spent in the system is going to be the average time spent in the queue waiting plus 1 over mu, and the probability the unit has to wait for service is going to be lambda divided by mu. So let's take a look at this in Python here. So we're looking at constant service time, and here we have that lambda equals 3, so we have 3 customers coming in, and we can service 6 per day. All right. So in this case, we are using pandas as PD, lambda equals 3, mu equals 6, and we're going to create our function, which is single serve, and then we're having that constant service time. So we would use this constant service time if, say, the process was automated. So maybe we have a system where we're doing maintenance on equipment, and so you simply get put into the queue to have the update happen to the equipment, but it's an automated process, so it doesn't vary from unit to unit. So here, okay, so lambda equals 3, mu equals 6. We put our formulas into our function, single serve underscore con. We give it a lambda, we give it a mu. You'll notice here we have much simpler formulas when we have that constant service time. We're outputting these different measures, and then we got to make sure when we call the function that we call and name those particular things so that the names are attached to the numbers. Otherwise, you're just going to get a list of numbers with commas in between, and you won't remember which one is which. The other thing is to take a dictionary, create these variables and these values so we can create a nice little output here that shows us that in this case, the probability we're idle is 50%, which means the probability you're waiting is 50%. The average time in the queue here is just a fraction of a day, and the average time in the system is a quarter of a day. So if these are 3 per day and 6 per day, so 6 is how many the automated system can fix or update, and we are queuing in 3 per day, then you can see that there's very little waiting, and the average time in there is a quarter of a day. So we can adjust those, we can change those numbers to see how that changes. Let's just do one more here, and that is, what if you have a multi-server system with no wait option? So what if you can't actually have a queue? And so instead here we have multiple servers, but there's no ability for anyone to wait. And so in this system, think, well, we lose customers, right, if there's no way to line up in the queue. So pretend you manage customer service. If a customer service agent doesn't respond to the customer's call or isn't available at the help desk, how many customers will you lose? How many lines or how many customer service agents will be busy? With this multiple server with no wait option, even though our service times are arbitrary, so when you look at these formulas here, as I just slide in, we can make it so there is a mu, there is an average for the service time, for the service per day or per week or whatever it is, and then we can have sigma. Do we have sigma in these functions? What do we have? We have, in this scenario, we have, so even though there can be variability in the service time, a lot of this changes because that there's no one in the queue, right? So that means the average time spent in the system is already known as 1 over mu. And we can see that here. The probability the system is idle is going to depend on how many servers we have. And so you can see that here. The probability a certain number of units are in the system is going to be a function of lambda and mu as we go through the number of servers. And J here is going to be the number of units in the system. The average of number of units in the system being served is going to be lambda over u times 1 minus whatever the number of units are in the system. So it really depends more on how many servers are busy because there is no wait here. So if you had a system where you had no way to wait, there was no way to line up, or there was no, then we can look at how idle the system is in our process here. All right, so let's take a look at how to do this. Let's go to Python. No waiting. Import pandas as PD. Import math. We need that math because we do have that factorial. And again, in this formula here, we are doing a sum. So we're going to do this sum. I'll just zoom in here. To do this sum, we are doing it from 0 to k. So we're just going to treat it as a loop. And we're going to loop through 0 to k, and then we're going to just add them all together. Okay, so that's how we're going to do that particular portion of the formula. You can see that here. We are for x in range 0 to k plus 1, because remember, ranges go up to but not including, and we want to sum all the way to k. So then we're going to do that, and we'll sum up as we go through that loop. So we're going to create this empty list. We're going to do our calculation for our multi-serve probability here, and I'll put that information. So we're amending the multi-serve formula to match here. All right, so where's this formula? So what we're doing here is we're looking at this formula here, the probability that a certain number of units are in the system, this calculation there. Okay. So if lambda is 3, if we can service 3 people, or sorry, 3 people come in a day, 6 people can be serviced in a day, and we have 2 servers, 2 people managing, then we can take our multi-serve prob that we have here. So this is taking that loop to see what's the probability that we have 1 person being serviced, 2 people being serviced, or no people being serviced. There's no queue here, so you either have your servers busy or idle. And so what is that probability? We're calling this again, this is the formula here, the probability that a certain number of units are in the system. All right, so what we can see here is that in this particular case where we have 3 people coming in for service and we can manage 6 per day, that really 62% of the time we're idle. Okay, 31% of the time one of the servers is busy, and 8% of the time 2 people are busy. So in this case, if there's no ability to queue or wait, then what we want to see is that we are covering the majority of, we have enough servers available so that people are not just turning away. And you can see that here, right? These are being filled here. If when we ran this, instead, we were seeing that all of our servers were busy all the time, we either need to create a system where they can wait, or we need to add more servers. Now, we can do the probability, so we can take these probabilities here, these p sub k, And what we do in the formulas here is you can see this average number of units in the system being served is a function of the probability of a certain number of units, this piece of K. So we can find that average number of units in the system being served by taking that formula, that's this one here, based on these probabilities. So we can run that here, and we can get this here. So what we have here is that if we go back to our formulas, we can look at the average number of units in the system being served, dependent on the number of ones in the system. So we can see here that 46% of the time we have, my goodness, getting tired here. Average number of units in the system. So this is the percentage of the time that we have 2 in the system. This is 46%. Number of times we have 1 in the system, 35%, and then 19% we have none in our system. So really when it comes to the no weighting, we really just need these last 2 formulas here. The other 2s really aren't relevant. Probably the certain number of units are in the system, and then the average number of units in the system being served. So we can do those 2. Really what we're looking at is, are all of these servers busy all the time? Do we need to add more servers? Or are we able to cover everybody without a queue? Or should we be adding a queue?